Welcome back to The Explainer. I am absolutely thrilled you're here today because, well, we're tackling a topic that sounds incredibly intimidating at first, but is actually remarkably intuitive once you get the hang of it. Okay, let's just dive right in. We are demystifying object-oriented programming, or OOP for short. Even for experienced developers, the massive wall of dense computer science jargon, things like polymorphism, encapsulation, inheritance, it can sometimes totally obscure the actual logic underneath. But today, our goal is to decode OOP by completely tossing aside all that impenetrable jargon. Instead, we're going to use the single most powerful learning tool we have, which is real-world analogies. By the end of this explainer, you are going to see that this programming paradigm isn't some abstract floating mathematical theory. It's actually incredibly grounded in reality.
So I want you to do something for me right now. Just take a quick second and look around the room you're currently in. What do you actually see? You don't see raw data, right? You don't see ones and zeros floating around in the air like the Matrix. You see real, distinct objects interacting with one another. Your laptop sitting on the desk, maybe a cup of coffee, your chair, a window. Object-oriented programming simply matches how our human brains already process the world. It lets us group things into these distinct, real-world entities. Because objectively speaking, everything is an object. And when we code using OOP, we are quite literally just mirroring reality. We're taking the completely natural way we categorize our physical surroundings and translating it directly into computer logic. Honestly, it is just that straightforward.
All right, let's break down the anatomy of these objects. In the real world, and in the exact same way inside a computer's memory, every single object has two main parts: state and behavior. Take the student we're looking at here as an example. Inside that student lies an entirely private state of mind. Maybe they're completely focused on the lesson, or, maybe they're off daydreaming about lunch. That private state includes things like their attention level, their mood, their current knowledge. Now, I can't directly reach in and rewire their brain to force them to pay attention, right? I have to interact strictly through their public interfaces, so their eyes, their ears, their expressions. The methods they use to interact with the world are things like listen, read, and speak. Imagine I suddenly announce a surprise pop quiz. Bam! I'm setting an input signal directly to their listen interface. That immediately triggers some internal logic and instantly mutates their private state from daydreaming to panic. And there you have it. That is state and behavior in action. A vending machine is honestly the perfect everyday example to see how this all builds together. On one side, we have the internal state, which essentially acts as our data. For a vending machine, this state consists of how many snacks are actually left on the coils, the internal temperature of the cooling unit, and of course the cold hard cash sitting locked safely in the vault. This is strictly private information. On the flip side, we have the public interface, which represents our methods or our behaviors. These are the tools the machine actually gives you to interact with it: the selection buttons, the coin slot, and, that highly satisfying refund lever. The machine keeps its data strictly private and only allows updates through very specific, well-defined public actions.
So the absolutely crucial point here is this idea of strict boundaries. Programmers call this encapsulation. Think about it. If you want a bag of chips from that vending machine, you can't just magically phase your hand through the front glass to grab it. If you actually tried that in the real world, you just break the glass. In the programming world, attempting to directly access another object's private state throws a massive error, famously known as an illegal access exception. There's no way around it. You have to play by the rules. You absolutely must interact with its public interface by inserting your money and pushing a button. The machine then encapsulates its own logic. It internally checks if you paid enough and if the chips are actually in stock. If everything computes, it dispenses the snack and updates its internal cash count entirely on its own terms.
And this brilliantly illustrates exactly how we transition from the physical world right into the digital one. An object-oriented program is basically just a collection of well-encapsulated objects, each with a name, attributes, and behaviors, interacting by sending messages back and forth to each other. Below that conceptual diagram, we can see our Java code. But here is the big secret. This code is really just a blueprint. It's titled vendingmachine.java. This text file simply defines what variables and actions a vending machine will have. It maps out the logic, but, and this is super vital to understand, it hasn't actually created a real physical machine in the computer's memory yet. It's essentially just the architectural drawing sitting flat on a desk. Let's quickly break down that blueprint to see how incredibly literal it actually is. Our physical internal state translates directly into code under section 1, our attributes. See that? We have int item stock equals 10 and double balance equals 0.00. That's literally just the machine keeping track of its snacks and cache. Then, our physical public interface, the coin slot and the buttons, translates perfectly into Section 2, our methods. We have void insert coin and void press button. When press button is called by a user, the code checks if the balance is greater than $2 and if the stock is greater than 0. If so, it dispenses an item and deducts the stock. The code's syntax perfectly, one-to-one, mimics the physical actions.
Okay, let's really dive into this next part, because this right here is the central aha moment of our entire explainer. We need to clearly define two words that get thrown around constantly in programming: class and object. A class is the blueprint, the template. It's that vending machine.java file we just looked at. It defines what attributes and methods an object will have, but it doesn't take up any physical data memory on its own. An object, however, is the real working instance created directly from that class. It takes up actual physical space in the computer's memory, specifically on a space called the heap, and it holds its own real unique independent values. So just think of the class as the factory patent, and the object is the actual physical machine humming away in your hallway.
Let's see how this all builds together when we actually turn our blueprints into reality inside our main.java file. This is where the magic happens. Look really closely at lines 4 and 8. We use a very special, very powerful command in programming, the new keyword. By typing new vending machine, close parentheses, we are actively telling the computer, hey, go look at that blueprint we made earlier and build me an actual working machine right now in memory. And notice we actually do it twice. We create object 1, which we cleverly call library VM, and set its physical location to library first floor. Then we create object 2, called cafeteria VM, and we put it in the student cafeteria. We now have two entirely separate living entities operating inside the computer.
Let's trace the execution of this code step by step to prove just how powerfully independent these objects really are. Step 1. We manufacture the library machine. It starts with a completely fresh state, 10 items in stock, and a $0 balance. Step 2. We manufacture the cafeteria machine. It also starts with its own entirely fresh state of 10 items and a 0 balance. Step 3. Now a student walks up to the library machine only. In the code, we simulate this by calling libraryvm.insertCoin $2.50 and then libraryvm.pressButton. The code runs, the library machine processes its own logic, dispensing the item and perfectly updating its own internal state.
Now I really want you to pay attention to a crucial data point here, the number 10. Down on line 16 of our code, we decide to check in on the cafeteria machine. We ask it to print out its item stock, and the output? It's 10. Even though the library machine just had a whole transaction, took in money, and dispensed an item, the cafeteria machine's snack stock remains completely 100% untouched. And that right there is the crux of why object-oriented programming is so powerful. Because of encapsulation and independent state, you can have literally thousands of objects interacting in a massive program without them ever accidentally messing up each other's private data. They're totally isolated, secure, and incredibly reliable.
Which brings us to our final thought for this explainer. We've seen exactly how OOP keeps an object's internal state strictly private, only ever allowing updates through well-defined public actions. It's literally the ultimate foundation of clean architecture and good coding etiquette. But you know, if everything in code is an object with a private state and a public interface, it begs a rather human question, doesn't it? How well are you protecting your own internal state? Are you letting every single external input immediately mutate your mood? Or do you have a well-defined public interface to process all that daily noise? It turns out good software design might just be pretty good life advice too. Thanks so much for joining me on this explainer today. Remember to keep your interfaces clean, and I'll definitely catch you next time.